Hello, and thank you for attending. My name is Santiago Lozano, and I am presenting on behalf of SENER Aeroespacial. This presentation is called MIA, European Multipurpose Space Platform Using cFS and Time and Space Partitioning. So, the presentation is mainly divided into 6 sections. In the first one, we will briefly present what MIA is and the context in which it was born, as well as some concepts of the European space market that apply to MIA. In the second section, we will look in more detail at the different layers that make up the MIA architecture. Then we will explain the SENER Service Layer API, one of the most important layers of the architecture, in which NASA's core flight system plays an essential role. We will also explain the workflow imposed by the use of MIA, the demonstrator that is being used to develop and test the architecture, and finally we will present the conclusions of the presentation and the next steps to follow in the near future. Okay, so let's start with a brief introduction to put you in context by answering 3 questions. The first question is, what is MIA? Well, it's not easy to give a short answer because MIA encompasses many concepts, but we can say it is a flexible solution from which to develop new space applications. And this includes, among other things, a modular multi-layer hardware-software architecture and a software development kit to develop applications on top of MIA. But we will go into more detail on this in the following sections. The second question would be, where does MIA come from? MIA has been designed and developed in the framework of a Spanish project called Madrid Flight on Chip. The project is funded by the European Union and the Community of Madrid and is coordinated by SENER Aeroespacial. But along with us, a number of companies and research centers of the Madrid metropolitan area are participating with the aim of boosting the region's economy in the design, development and launch of small sats. Note that because of this, MIA was born with the vocation to operate in the European space sector, whose legislation is slightly different from that of the United States. For example, in Europe, we are guided by other standards for aerospace engineering, the ECSS, which stands for European Cooperation for Space Standardization. And in fact, MIA implements the European Packet Utilization Standard, which is the standard used to communicate different units of a space system according to the ECSS. However, the modularity with which the architecture has been designed could allow its CC adaptation to any other software project. The third and last question could be, why is MIA necessary? Some of its main advantages are to lighten and lower the recurrent development costs of small space platforms, since MIA encourages the reuse of much of the architecture between different missions. It also allows an easy integration of third-party applications by standardizing the interfaces against which these applications are developed. And this last feature has another side effect that we think is very beneficial because it lowers the barrier to entry into the industry for small and medium-sized companies. You may wonder, how is this achieved? Well, mainly because of MIA's architecture. MIA proposes a multi-layer and modular architecture in which software and programmable hardware are divided into separate blocks that communicate with each other through a common and standardized interface. From bottom to top, in the diagram you can see in the slide, the bottom layer, the first layer, would be the hardware layer. MIA is developed to run on system-on-chips and multiprocessor system-on-chip targets, so this layer includes the typical elements that a SoC has, processing cores and FPGA, memory devices, interconnect logic, and other peripherals. On top of the hardware layer, we have the time and space partitioning layer. The main component of this layer is a hypervisor, and it is of vital importance because it allows the deployment of different partitions or virtual machines and guarantees total separation between them. This allows applications of different criticality to run on the same platform, which, remember, is a multiprocessor system on chip, so it has a great processing capacity. Because the operation or even the potential failure of a less critical partition could not affect the nominal operation of the more critical partitions. This is what is commonly referred to as mixed criticality application deployment, and is what this layer allows us to do. Currently, we are using Extratum Next Generation, a Spanish hypervisor that is being used in several European projects on the Xilinx 7000. An operating system can be deployed on each of the hypervisor partitions. Currently, we are using Linux and have also performed some tests with Artemis. And of course, in addition, the hypervisor also allows running partitions that do not use any operating system, which could, for example, make it easier to ensure determinism of critical applications. Above the operating system layer, we would have the service layer. Basically, this layer implements all cross-cutting functionality for different space missions. This has a dual purpose. On the one hand, of course, to avoid re-implementing basic system functionality from one mission to another. But on the other hand, by always accessing this basic functionality through this layer, the development of applications running on it is standardized. Currently, we have leveraged the power of NASA's Core Flight Executive to implement this layer. We will see this in a little bit more detail later, but we will also see in a minute that we use an abstraction layer so as not to rely on specific calls to the Core Flight Executive functions. And finally, the top layer is the application layer, which is where the mission-specific functionality is implemented. Note that up to this point, the platform is generic and multi-purpose, and this layer is the only one that should differ from mission to mission. In addition, as mentioned previously, to avoid relying on a specific hardware target or a specific operating system or even a specific framework such as the Core Flight System, MIA includes a number of abstraction layers. The operating system abstraction layer separates the services layer from the operating system. The board support packages and the platform support packages abstract the rest of the architecture from the hardware-specific functionality, and the SENER service layer API separates the application layer from their services layer and therefore from the rest of the architecture, from all the bottom layers. The operation of these abstraction layers is similar, which is mapping specific calls to functions of an operating system or the Core Flight Executive, for example, to generic calls, which are used by the rest of the architecture components. In this fashion, for example, if a new operating system is introduced in the future, the rest of the architecture would not have to be modified, and applications developed for previous missions could continue to be used. Among these abstraction layers, the SENER service layer API is of special importance because of where it is located in the architecture. The SSLA acts as a proxy, exposing the services and functionalities of the platform to the applications in a systematized and standardized way. In this way, applications are protected both from specific implementation details, like for example the Core Flight Executive or the FPGA logic or standards such as the Packet Utilization Standard, and from the impact of modifications in the lower layers of the architecture. The SSLA is therefore the single entry point for accessing both software services and services implemented in the FPGA. On the one hand, this reduces the complexity of the application developer's task, who has a single interface to program against. In that sense, programming applications to run on MIA resembles the development of mobile applications, for example, so that a whole app store compatible with the platform could be progressively built as we use the platform. And on the other hand, having the services that you expose and how you expose them well defined allows you to have a precise control over the information shared with third parties. Now we will briefly review some of the advantages of the workflow that comes with the use of MIA. Of course, for the development of MIA, we take advantage of all the fantastic features offered by the continuous integration tools we already know, but we wanted to go a step further by adding hardware-software integration to the work cycle. Traditionally, the interfaces between the software and the programmable hardware implemented on an FPGA were defined in a document that is shared between the software and FPGA development teams. Keeping these two teams synchronized is not only costly, but can easily lead to errors if changes in any side are not correctly reflected in the document. With MIA, this integration is done automatically thanks to the power of the continuous integration pipelines. When a new version of the programmable hardware is sent to the repository, not only is a new version of the bitstream automatically generated, but, and here is the key, the software libraries and drivers needed to access the implemented hardware functionalities are also generated. For example, if the FPGA team decides to flip 2 bits of a register or add a spare byte or something like that, applications using the register are not affected by this change. The software library will adapt the structures and functions of the libraries to protect the rest of the software from changes. The continuous integration pipeline also generates an interface control document intended to function only as report information, and I mean by only that it is no longer used as an input for software design. Okay, this is a small demonstration video. As you can see here, let me see if I can point it. Yes, we have 2 folders. The first one is the inputs folder, where we can find the hardware description of all the FPGA blocks, the IP blocks that we are going to use. And the second one, the SSLA lib, is the output folder, where both the source code of the drivers and the interface documents for each IP will be auto-generated. So let's continue with the video, if we might. In the output folder, you see there is only a structural code, no other code or document related to the IPs in the FPGA. So we launch the script. And you will see in a moment that both the interface documents and the drivers are generated. We can see here the interface documents. This is only, remember, for reporting purposes. And I mean by that this is not an input for software design, because we have automatically obtained the drivers for that. And here you can see the drivers for each of the IP blocks in the FPGA. Regarding the development cycle, we can distinguish two levels of abstraction: system level and development level. At the system level, the cycle starts with the definition of the hardware architecture, and then the allocation of the different functionalities to software modules or IP blocks on the FPGA. In the case of the functionality to be implemented in the FPGA, after designing the blocks and the interfaces they offer, the automatic process of continuous integration generates the necessary libraries to use these IP blocks. At the development level, therefore, the FPGA and software teams can work in parallel, feeding back through continuous integration cycles. The creation, deployment, and testing of software applications is also facilitated by the use of a wizard. For creation, the wizard builds the entire application structure and telecommands based on configurations, leaving the developer to code only specific functionalities. The wizard also allows the code to be easily deployed on the hardware, and for each application and command generated, the wizard also auto-generates test functions to verify them. To illustrate all this, we will now watch a video demonstration of application creation. The demonstration involves three elements: a peripheral unit, in this case an inertial measurement unit, the board to which it is connected, and a remote PC that will send telecommands to the board. From the inertial measurement unit, we are going to make use of a simple test register, readback, which simply allows us to write into it and to read back the same value we have written. In the target board on which MIA runs, two applications are generated with one command each. The IMU write application, which will respond to a command by writing to readback. This will write the value of a counter that will increment by 1 for each write. And the IMU read application, which will respond to a command by reading the register readback. On the remote PC, the test scripts that have been auto-generated for each command will be launched. Okay, so this is the demonstration video. As you can see, the wizard we are talking about has been developed as an extension for Visual Studio Code. And I think it's also worth mentioning that it allows to debug directly on the real hardware. So it allows to use breakpoints on the GDB server, for example. Let's continue with the video. As we said, we are going to create an SSLA project. So we import the SSLA library generated specifically for this project, using the automatic process that we have seen in the previous video demonstration. So note that each project will have different IPs. We can see here all the imported IPs and their corresponding associated functions, such as, for example, AXI2 telecommand and AXI2 IMU. After importing, we can now create and configure our applications. We will start by creating and configuring the IMU read application. And we'll do the same for the write application. After that, we can now create and configure the corresponding telecommands. So note that up to this point, the developer has not coded anything. He has simply generated the structure of applications and commands through the wizard. Let me stop the video. Now what he has to do is to complete with code what he wants each command to do. When you click on each command, the wizard redirects you to the code area to be completed. So we can complete now the functionality of the read-readback command. Each function has an associated snippet that helps the developer to make the process more intuitive and fast. And we complete also the functionality to write readback command. We add the counter ++ so that the write value changes on each call. So now we begin with the deployment phase. We select the path of the cFS and the type of linking desired, static or dynamic. And we start with the build of the whole project. And we load it on the card on our target. From here you can see the program running on the board. I can point you here with the laser, yeah. Here and here we have our brand new 2 applications running along with all the core flight executive functions. And we open another terminal to launch the test scripts previously generated for each of the commands. So we are going to trigger the applications following the cycle write, read, write, read. So you can see here the events generated for each application and command. Finally, let's have a look at the use case we have used to test MIA. As mentioned previously, we deployed MIA on the Xilinx Sync 7000. So this diagram shows the 2 domains of the board, the processing system and the programmable logic. Thanks to the modular architecture of MIA, the blocks, both software and FPGA, are conceived as interchangeable modules connected through a bus. Our use case is a fully functional satellite, so the FPGA connects to various sensors and actuators. Note that we use the FPGA for input-output processing, mainly to have less real-time requirements in the software domain. The software applications created interact only with the SSLA to access both the programmable logic and the platform services, which are based on NASA's Core Flight Executive. In this fashion, as we have already seen, the developer is abstracted from specific hardware or software implementation details. This is just a brief summary of something we have already seen. The elements we use in each of the layers. We use the Sync 7000 as a deployment board. We use Extratum Next Generation as a hypervisor. We use Linux, and we are also testing Artems as operating systems. We use the NASA's Core Flight Executive for software services, and the PUS, the Packet Utilization Standard Library, which allows us to comply with the European standard for units communication. To conclude, let's quickly review some of the problems that MIA addresses and what parts of the architecture solve them. The architecture, due to its power and versatility, allows us to efficiently perform hardware-software co-design and to balance the load between hardware and software thanks to the use of configurable FPGAs. In addition, the time and space partitioning allows us to deploy applications of different criticality on the same platform, allowing us to take full advantage of the processing capabilities of the system on a chip. We obtain high reusability in all the components of the architecture thanks to the abstraction layers, with which we clearly separate the mission-dependent code from the non-mission-dependent code. This translates into a reduction in both design and development costs and time to market. The SSLA, in particular, allows us to easily integrate third-party applications. Note that as part of Madrid Flight on Chip, the project in which MIA is developed, we had to integrate software and hardware modules from other companies, so we have been able to test this feature. Our wizard provides a development environment that abstracts the user from the details they don't need to know. And by constantly integrating hardware and software development flows, we are also able to reduce or detect at an early stage at least integration errors. Also, as we said, we are already using MIA in some of our projects, so it will continue to mature and expand in the coming months. So that's all from my side. Thank you very much for listening, and please, if you have any questions, do not hesitate to contact me by email. You have it there, santiago.lozano@aeroespacial.sener. If I can't answer a question, I'm sure I can redirect you to the person on the team who can.